After studying this module, you shall be able to learn about testing of significance of estimators, identify the dependent variables that significantly contribute towards the determination of dependent variable, build confidence intervals for population parameters, analyze the overall significance of fitted module using an F test. Hypothesis testing in a two-variable regression. So far, we have learned how to calculate and interpret the intercept and slope coefficient in the simple two-variable regression analysis using the OLS and the MLE method. Moreover, we are now in a position to also determine the goodness of fit of the regression line. Goodness of fit is measured using the concept of standard error of estimate SEE, or a more standardized concept of the coefficient of determination, which is the square of the coefficient of correlation. In this module, we would move from the branch of statistics that deals with estimation to that part which deals with statistical inference. Here, we will learn to conduct hypothesis testing for the significance of slope and the intercept estimators and construct confidence intervals for defining the limits wherein the corresponding population parameters are expected to lie. 3. Hypothesis testing. Hypothesis testing for the OLS estimators. Now we are in a position to determine the sample regression function SRF, understand its properties and interpret it. But our objective function is to determine hypothesis about the population parameters. For this, we require a structured approach to test the significance of the intercept and slope coefficients of the SRF. For this, we need to know how the intercept B0 and the slope coefficient B1 of the SRF are distributed. At this stage, we make an additional assumption that the error term mu I is independently and normally distributed with mean 0 and variance sigma square, that is mu 1 is NID 0 sigma square, where NID is normally and independently distributed. We require the normality assumption because it is the property of normal distribution that states that a linear function of the normally distributed variable is also normally distributed. We know that B0 and B1 are linear functions of mu I. Therefore, if mu I is normally distributed, then we can assume B0 and B1 also to be normally distributed. B0 approximately equal to n of B0 comma sigma square B0 and B1 is equal to n of beta 1 sigma square B1. It further implies that the dependent variable y would also be normally distributed, as it is a linear function of mu I with mean equal to beta naught plus beta 1 x and variance sigma square, that is yi is approximately equal to n of beta naught plus beta 1 x comma sigma square. Hypothesis testing involves 3 steps: stating the null and alternative hypothesis, finding the value of test statistic, deciding the decision rule to accept or reject the normal hypothesis, setting null and alternative hypothesis. While we test for the OLS estimators, our objective is to know whether the slope and the intercept estimators are statistically significant or not. Herein, we compare the intercept estimator B0 with a value of population parameter B0 taken to be 0. When we set the null hypothesis at H0, B0 equal to beta naught is equal to 0, or simply H0 beta naught is equal to 0, we are hypothesizing the intercept term equal to 0 or is statistically insignificant. Alternatively, the alternative hypothesis is a complete contradiction of the null hypothesis and would be stated as H1 B naught is equal to beta naught not equal to 0 or simply H1 beta naught not equal to 0. Here we imply that the intercept term is statistically significant or significantly different from 0. Note that the intercept values may not always be equated to 0, they may be hypothesized against some value known a priori or in advance, as there may be a theoretical justification to it. Likewise, we can set the hypothesis for the slope coefficient as H naught B1 equal to beta 1 equal to 0, null hypothesis H naught B1 equal to beta 1 not equal to 0, alternative hypothesis. Here again we are testing whether the slope coefficient is statistically significant when beta 1 is not equal to 0 or beta 1 equal to 0. When we set the null and alternative hypothesis as above, we would be dealing with a two-tailed test or to prove the significance of the parameter in question. However, if we need to test whether the slope coefficient is positive or not, then the hypothesis set would be H naught beta 1 less than equal to 0, H naught beta 1 greater than 0. The null hypothesis states that the slope coefficient is not positive as against the alternative hypothesis, that is that it is positive. Such a framing of hypothesis calls for a single tail test. The above is an example of a right tail test. If the hypothesis was, however, reversed, that is, we had to find out whether the slope coefficient is negative or 0, the hypothesis would be H naught beta 1 greater than equal to 0, H naught beta 1 less than 0. This calls for a left tail test. The distinction between these tests would be clear once we study the decision rules in details. Test statistic. We know that beta naught is equal to n of beta naught sigma beta b square and b1 is equal to n of beta 1 sigma beta 1 square. If we subtract mean or expected value of the estimator from the estimator and then divide by standard deviation, the estimators b0 and b1 would behave like standard normal variates following a normal distribution with mean 0 and standard deviation called here as standard error as SE b0 and SE beta 1 respectively. But we seldom know the population variance of standard deviation. This has to be approximated by SE b0 and SE b1 respectively, that is by the standard error of estimators. Therefore, while we define the test statistic, we would be grappling to define two unknown quantities beta naught and beta 1 in the numerator and SE beta naught and SE beta 1 in denominator. Kindly note, when ratio of two unknowns is involved, the distribution that the estimator follows would be a t distribution with n minus 2 degrees of freedom, as there are two estimators. T distribution is a small sample distribution that tends towards the normal distribution when n approaches infinity. The t statistic for two estimators would be t beta naught is equal to b naught minus beta naught upon SE b naught, that is equal to sample statistic minus population parameters upon standard error of simple statistic. We already know SE b naught is equal to square root of sigma xi square upon n into sigma small xi square into sigma. T beta 1 slope estimator is equal to B1 minus beta 1 upon SEB1. SEB1 further is equal to sigma upon square root of sigma xi square, where sigma is approximated by sigma naught is equal to square root of sigma ei square upon n minus 2. Decision rule. For the decision whether to accept or reject the null hypothesis, we compare the calculated value of t statistic obtained in 2 above with the critical value of t obtained from t tables. But before we determine the table value, we need to state the level of significance alpha. The level of significance is the probability of committing a type 1 error, that is rejecting the null hypothesis when it is actually true. In other words, it is the probability of taking a wrong decision. If alpha is equal to 5%, it implies that we would be taking a wrong decision as stated above in 5% cases. In a two-tailed test, this 5% is equal to 0.05 is split into 2 and rejection region kept in the two tails of a normal distribution curve. For a two-tailed test, if mod of Tc is greater than T star, we are in the rejection range and would reject the null hypothesis. For a right-tailed test, the entire rejection range would be in the right tail. For a left-tailed test, entire rejection range would be in the left tail. Hence, if Tc is less than minus T alpha star, reject H naught for the left tail. Let us try to understand hypothesis testing with the help of an example. For a relation between per capita savings and per capita personal income, the following results were obtained for US for 32 years. ST is equal to 384.105 plus 0.067 YT. R square is equal to 0.538. Then we have two figures in the bracket, 151.105 and 0.011. Figures in the brackets are standard errors. We need to test the significance of both the intercept and the slope coefficient. ST is equal to per capita savings and YT is equal to per capita personal income. Let us test significance of the intercept test first. Step 1, H naught, B naught is equal to 0, intercept coefficient is insignificant. H naught, B naught is not equal to 0, intercept coefficient is significant. Step 2, let us set the levels of significance, alpha equal to 5%, and step 3, test statistic. T beta naught is equal to B naught minus beta naught upon SEB naught. This is equal to 384.105 minus 0 upon 151.105. This is equal to 2.54. Step 4, decision rule. Since we adopt a two-tailed test to the above question because of not equal to sign in the alternative hypothesis, we set aside alpha by 2, that is 0.05/2, which is equal to 0.025 area in the rejection range on both tails of a normal probability curve, with DOF, the degree of freedom, is equal to n minus 2, which is equal to 32 minus 2 is equal to 30. The critical value as obtained from the T table is plus minus 2.042. Therefore, if the calculated value of T beta naught lies between minus 2.042 to plus 2.042, we are in the acceptance range, otherwise in the rejection range. In this case, we would reject the null hypothesis. Step 5. Accepting alternative hypothesis implies the intercept coefficient is significantly different from 0. Likewise, to test the significance of the slope coefficient, we follow the same set of steps as above. Step 1. H naught beta 1 is equal to 0, slope coefficient is insignificant. H1 beta 1 is not equal to 0, slope coefficient is significant. Step 2. Alpha is equal to 5%. Step 3. T beta 1 is equal to B1 minus beta 1 upon SEB1. This is equal to 0.067 minus 0 upon 0.011. This is equal to 6.09. Step 4. Critical value is same as above for a two-tailed test for alpha equal to 0.05 and degrees of freedom equal to 30, T star is equal to plus minus 2.042. Step 5. T beta 1 is greater than mod of T star. We reject the null hypothesis and conclude that the slope estimate is also significant. A look at the above examples tells us that higher the value of calculated T statistic, the greater would be the possibility for it to lie in the rejection range. Therefore, there being a higher possibility for the estimators to be significant. One way to decide whether to accept or reject the null hypothesis without actually looking at the T table is the 2T rule of thumb. This rule applies for 20 or more degrees of freedom and for level of significance alpha is equal to 5%. It states that we can safely reject the null hypothesis if the calculated value of the T statistic exceeds 2 in absolute value. Confidence intervals. Having tested the statistical significance of the two regression coefficient beta naught and beta 1, we can go ahead to determine the intervals within which the corresponding population parameters are expected to lie. In order to establish these intervals, we use a property of normal distribution that states that mean plus minus 1 sigma, where sigma is the standard deviation, covers 68.7% data, mean plus minus 2 sigma covers 95.45% and mean plus minus 3 sigma covers about 99.7% data. Confidence interval of the intercept of coefficient beta naught. Beta naught can safely be considered to lie between lower limit beta naught minus T alpha by 2 SEB naught and the upper limit B naught plus T alpha by 2 SEB naught. Therefore, beta naught is equal to beta naught plus minus T alpha by 2 SEB naught is the 100 into 1 minus alpha % confidence intervals for B naught. If we are testing the hypothesis at a level of significance alpha is equal to 5%, we are 95% times sure that population intercept term would lie between the limits specified above. T alpha by 2 is nothing but the critical value of the T distribution we have learned to calculate above. Likewise, we can also say that probability given below that the calculated value of T statistic beta naught lies between two critical limits minus T alpha by 2 and plus T alpha by 2 is 95%. That is, PR is equal to minus T alpha by 2 less than equal to T B naught is less than equal to T alpha by 2. This is equal to 1 minus alpha. If we wish to determine confidence limits for B naught in the savings income example, above we get beta naught is equal to B naught plus minus T alpha by 2 SE B naught. Substituting the values, this becomes equal to 384.105 plus minus 2.042 multiplied by 151.105, which is equal to 384.105 plus minus 308.51641. Confidence limits are 75.548 less than equal to beta naught is less than equal to 692.66. As per our interpretation, the true value of intercept term is likely to lie between 75.548 and 692.66 in 95% cases. Confidence interval for slope coefficient beta 1. Similarly, the confidence interval for beta 1 is mathematically stated as beta 1 is equal to B1 plus T alpha by 2 SE B1. This is equal to 0.067 plus minus 2.042 multiplied by 0.011, which is equal to 0.067 plus minus 0.02246, which is equal to 0.0445 and 0.08946. The slope coefficient is likely to lie between 0.0445 and 0.8946 in 95% cases. 4. Analysis of variance A NOVA for regression. In regression analysis, we have so far learnt to determine and express the quantum and the nature of relationship between the dependent y and the independent variable x. The tests of two hypotheses using above help us to determine whether the intercept and the slope coefficients are significant or not. There is another technique which helps us to determine the overall significance of regression module. We can learn this approach once we learn to decompose the total variation in the dependent variable into its causes. The presentation of this decomposition is often summarized in the ANOVA table. We have already learned that the total variation in y can be decomposed into two components, one due to regression, this is the bottom portion that is explained, and the second due to residuals, the portion that is unexplained. Following is the construction of ANOVA table. Source of variation, sum of squares, formula, degrees of freedom, and mean sum of squares MSS. Number 1, due to regression. ESS explained sum of squares sigma yi square is equal to bi square sigma xi square. Degree of freedom 1 k minus 1. ESS slash 1. Due to residuals, RSS residual sum of squares sigma ei square n minus 2 n minus k RSS slash n minus 2. TSS total sum of squares sigma yi square n minus 1 into n minus k minus 1, where k here stands for the number of parameters to be estimated. Since we are discussing a two variable regression, k is equal to 2. Total sum of squares TSS is equal to sigma yi square, which is equal to sigma yi minus y whole square. Therefore, to calculate this, we lose 1 degrees of freedom while calculating, and degrees of freedom hence are n minus 1. We already know the degrees of freedom for RSS sigma ei square is equal to n minus 2. This is because to calculate the residual, we first need to calculate the estimated value of y cap, for which the two regression coefficients need to be calculated. We therefore lose 2 degrees of freedom in the process. The degree of freedom for ESS can be calculated as the balance or difference between degrees of freedom of TSS and degrees of freedom of RSS. The F statistic is defined as the ratio of the mean sum of squares of ESS and the mean sum of squares of RSS. F is equal to MSS of ESS upon MSS of RSS. This is equal to B1 square sigma xi square / 1 upon sigma ei square / n minus 2. The F statistic would follow a F distribution with 1 k minus degrees of freedom in the numerator and n minus 2 n minus k minus 1 degrees of freedom in the denominator. This F ratio provides a test statistics to test the overall significance of the model. It tests the null hypothesis that all the slope coefficients are simultaneously equal to 0 as against an alternative hypothesis that they are not all simultaneously 0. In a two variable case, we have only one slope coefficient, therefore conducting a F test would be testing the null hypothesis that beta 1 is equal to 0. The calculated F value above will have to be compared with the relevant F table for the desired degree of freedom in numerator and denominator at a predetermined level of significance. As before, if F calculated value greater than F tabulated value or called critical value, we would reject the null hypothesis that all the slope coefficients are 0. Continuing with this example of savings income model where ST is equal to 384.105 plus 0.067 YT, R square is equal to 0.538, SE 151.105, 0.011 and n is equal to 32. We are also given explained sum of squares ESS is equal to 0.4425 and residual sum of squares RSS is equal to 0.358. If we need to test overall significance of the model using F test, we would proceed as follows. Step 1, setting of hypothesis. H0 B1 equal to 0, all slope coefficients are simultaneously equal to 0. Here we have only one. H1 beta 1 not equal to 0, all slope coefficients are not simultaneously 0. Step 2, level of significance alpha is equal to 5%. Step 3, F statistic. F statistics is equal to MSS of ESS upon MSS of RSS. This is equal to ESS/1 upon RSS/n minus 2. This is equal to 0.4425 upon 0.358/30. This is equal to 37.0801. Step 4, decision rule. Find the table value of F for 1 DOF in numerator and n minus 2 is equal to 30 DOF in denominator at an alpha equal to 5%. The corresponding value of F 1, 30 is equal to 4.17. Since calculated value of F is greater than critical or table value of F, we reject the null hypothesis. Step 5, the slope coefficients is not 0. The model is significant. This is the same result we obtained in the t-test. In fact, for a two-variable regression, f-test and t-test are analogous. It can be proved mathematically that in a two-variable case, the f statistic is equal to the square of the t statistic for the slope coefficient. That is, f is equal to t beta 1 whole square. This is because for the null hypothesis beta 1 is equal to 0, the t statistic is given by t beta 1 is equal to b1 upon SEB1. We know that SEB1 is equal to sigma naught upon under the root sigma xi square. Since population sigma is unknown, it is best approximated by its unbiased estimator sigma naught is equal to square root of sigma ei square upon n minus 2. Substituting in the above equation, SEB1 is equal to square root of sigma ei square upon n minus 2 multiplied by 1 upon sigma xi square. T beta 1 is equal to b1 upon sigma ei square upon n minus 2 whole multiplied by square root of sigma xi square. However, f statistic is given by f is equal to MSS of ESS upon MSS of RSS, which is equal to b1 multiplied by sigma xi square whole upon sigma ei square slash n minus 2. This value is clearly the square of t beta 1 obtained above. Hypothesis testing for estimators involves the testing of their significance at a predetermined level of significance, which is probability of committing a type 1 error. In hypothesis testing, a test statistic is developed. Its value is compared with the critical value table based on the nature of its sampling distribution T, F or chi-square. The critical values can be used to predict the confidence intervals within which the relevant population parameters are expected to lie. To test the overall significance of the model, a F statistics based on the ANOVA table is constructed. The test hypothesis, all slope coefficients are simultaneously 0 as against the alternative hypothesis that they are not. For a simple two regression model, the F statistic is the square of the relevant slope T statistic.